Hey there, folks. In this video, we are going to be simplifying radicals. So we're going to be writing radicals with the smallest numbers possible. Now, in order to do this, we are going to be breaking our radicals down into what is called prime factors. So prime numbers are numbers that can't be divided by anything other than 1 in itself. Examples of primes are 5 or 7, 11, things like that. So we want to break these things down into their prime factors, and then we're going to look for groups. Now here we have a square root. A square root kind of corresponds to something squared. A square root is the opposite of squaring something. This right here, this exponent that it kind of pairs up with, that's what we would call the index. So on a square root, you're never going to see it written, but there's technically a little index of 2. And we can see, kind of looking ahead, we're going to see indices of 3 and 4. So we'll tackle that when we get there. What I want to do is I want to break this number 63 into its prime factors by making a little factor tree, and I'm going to look for groups of 2 because that's my index. As soon as I have a group of 2, I can pull that number out. So let's get started. If I'm looking at the number 63, I need 2 numbers that go into 63. It does not matter which 2 I choose. So I know that, let's see, 3 goes into 63. And that would be 3 times 21. Now, 3 is a prime number. Ooh, that is a terrible 21. 3 is a prime number, so I can't really go any further. That means I need to keep going on the 21. Well, 21 could be a product of 3 and 7. So this thing is completely factored out. At this point, what I need to do is look for pairs. And I'm saying, hey, right here, I've got a pair of 3s. And then I've got this 7 kind of left all by itself. I'm only looking at the prime numbers when I do this. So when I write this as a simplified radical, what's going to happen is the number that got paired up will go on the outside. So I have a 3 that can go on the outside. And then the 7 did not have a partner, did not get paired up, so that stays in the radical. So the square root of 63 is the same thing as saying 3 times the square root of 7. And if you need proof, here we go. Square root of 63 is 7 point stuff. 3 times the square root of 7, guess what? Same exact value. All right, next one. 120. Again, I'm going to break this apart into prime numbers, and then I'll look for pairs because my index here is a 2. Even though it's not written, we assume it's a 2 if it's blank. Any 2 numbers that multiply to be 120. I've got a bunch of choices, 2 and 60, 3 and 40. I'm going to keep it easy. I'm going to go 10 and 12. Anytime something ends in a 0, I like to divide it out by 10. 10 can keep breaking down into a 5 and a 2, and those are both prime, so I can't really go any further. 12 can break down. I can do a 3 and a 4, a 2 and a 6. I'm going to do a 2 and a 6 because that's going to say we've got a pair right here. Awesome. I can keep breaking down the 6, though. That would be a 3 and a 2. And I can't really go any further on those. So when I go through and write this as a simplified radical, anything that got paired up will go on the outside. In this case, I have a pair of 2, so that comes out. On the inside, I have a 5, I have a 3, and I have a 2 that got left over. So if I were to multiply that out, 5 times 3 times 2, that would be 30. So 2 rad 30 is the same as saying square root of 120. On to square root of 48, x cubed y squared z to the 7th. Anytime you see variables, that's actually going to be easier to deal with, and we'll get to there. But first, let's go ahead, let's tackle the 48, and then we'll get to our letters. So 48, I'm going to break it apart into prime factors. Let's see. Let's go 12 and 4. So I have 4 and 12. Neither of those are prime, so I need to keep going. 4 can be 2 and 2. And that gives me a pair. 12 can be 3 and 4. And then 4 again is a 2 and a 2. So I've got a pair there. 3 is a prime, so I can't really go any further, so we're stuck. So So both of these can get pulled to the outside of the radical. 2 and a 2, that would make a 4, because I had two separate 2's. I'm going to leave some space here, because we might have letters filling in. And then I had the 3 that was kind of stuck left over, so a 3 stays inside. Now let's look at the letters. I have x to the third, so that's 3 x's. I have y squared, so that is 2 y's. Z to the 7th, holy smokes. Z, 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 a lot of z's. Why did I do so many z's? And just like before, I'm going to look for pairs. I've got a pair of x's. I've got a pair of y's. I've got a pair of z's, another pair of z's, another pair of z's. I've got an x left over and a z left over. So once I have that figured out, I have one pair of x's. I'm going to have x to the first power out here because that 1 represents one pair. I have one x that got left over, so leftovers stay inside. Right here, I have one pair of y's, so I have y to the power of 1. And if it's the power of 1, you guys don't need to write that. And there are no y's left over, so I don't need to worry about anything there. Z's, I have 1, 2, 3 pairs. So I will have z cubed, z to the third, but we also have a z left over, so that z would stay inside. This would be my final answer. Next one looks awfully similar. The only difference is we already have a 5 hanging out front, so that will kind of show up at the very end, and we'll tackle that when we get there. We'll first break down the 60. We've got 10 and 6, neither are prime, so we'll keep going. 10 goes to 5 and 2, 6 goes to 2 and 3. All right, I got a pair of 2's, so that can come out. Then I've got a 5 and a 3 left over, so that could stay in. 5 times 3, that would be 15. Now let's tackle letters. I have x squared. Well, that would be the same as having one x, one pair of x's. Y to the 5th, if I imagine 5 y's being written out, I can make 2 pairs out of that, but then I'd still have a y left over. So 2 pairs would be 4 of the y's, and we have the one left over. Z to the 10th, I can make 5 pairs out of that. Basically, I'm taking these exponents dividing by 2, and there's no leftover. So there's no z's in here. So at this point, the only thing I have to do is kind of take into account this 5 that we started with. So 5 times 2, all of this is 10. X, y squared, z to the 5th, rad, 15y. And that is my final answer. All right, these next problems are going to behave very, very similarly. The only difference now is we have different index values, different indices. So before with square roots, which represented something squared, where we're looking for pairs of numbers, we now have cubed roots, which is going to be the opposite of something cubed, which means I need to look for pairs or groups of 3, triples. Same thing here. I'm going to look for groups of 3. Over here, I need to find a group of 4 when we go through. So let's start off with a whole number 16. Let's start off easy. 4 times 4. Neither of those are prime. Let's keep going. 4 can be broken apart into 2's. This 4 broken apart into 2's. Now previously, if I was doing square roots, I'd have 2 pairs. However, it's no longer a square root. We have a cubed root, which means I need to find groups of 3. So here are 3 2's that can get pulled out of the radical. And left in the radical, I need to make sure I include that index, is this 2 that was left over. So that would be my final answer. If I do the cubed root of 128, x to the 4th, y squared, z to the 8th, we would break down 128. I don't really know what goes into that, so I know it's even. I'm just going to divide it by 2 to shrink the number down a bit. So if I divide by 2, I know 120 divided by 2 is 60. 8 divided by 2, so 64. 64 can go to 8 and 8. That's a weird looking 8, sorry. 8 can break down into a 4 times 2. Same thing. 4 can break down into a 2 and 2. I'm seeing a whole bunch of 2's. Oh boy. All right. So this thing is all factored out. Let's see, I've got a group of 2's here. Again, I'm looking for triples, right, because my index was 3. I got a group of 2's here. And then I have this 2 that's kind of left over. So I'll take these guys, both of these 2's, and that would be a 4 on the outside. This leftover 2 stays inside the radical. And now, just like we did before, we're going to tackle the numbers, or sorry, the letters. If I have 4 x's, so that's x, 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 I can make one group of 3, so I have x to the first power, with 1 left over, so I'll have x inside. If I have 2 y's, well, I don't have enough to make a group of 3, so I can't pull anything out, so this will stay as y to the second power in there. Then if I have 8 z's, z, 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 1, 2, 3, 4, 5, 6, 7, 8. If I have 8 z's, I've got 1 triplet, 2 triplets, 2 left over. So I'm going to have z squared to represent 2 groups of z's, and then my leftover z's right there. So that one's entirely done. For this, essentially what we're doing is we're taking these exponents and we're dividing by the index. And then if there's a remainder, that is your exponent here. So if you want a shortcut, 8 divided by 3 would be 2 with a remainder of 2. So we'd have 2 with a remainder of 2. 4 divided by 3 would have been 1 with a remainder of 1. So there is kind of a shortcut there. All right, last and final one, home stretch. Here we go. This time we are looking for groups of 4 because that is my index value. This is a 4th root. So let's start off. I have 2 times 16. When I factor this down, 16 can keep going, 2 times 8. 8 can keep going, 2 times 4. 4 can keep going, 2 times 2. Holy smokes, a lot of 2's. I am looking for a group of 4 of these. So 1, 2, 3, 4. With this guy left over. So this will turn into a 2 on the outside of the radical. I'm going to leave some space for the letters. Then we have the 4th root of a 2 left over inside. So now let's take a look at our variables. I have x to the 9th. If I were to split that into groups of 4, if I have 9 x's, that would be enough for 2 groups of 4. So that accounts for 8 of them. And then I'd have 1 x left over. If I have 3 y's, well, I don't have enough to make a single group of 4, so all 3 y's stay inside the radical. Here, if I have 7 z's, I have enough to make one group of 4. That accounts for 4 of the z's, but then I'd have 3 of them left over. That's a 3 right there. And that right there would be my final result. All right, folks, you know the drill. If at any point something did not make sense, please do not hesitate to reach out and let me know. I'll do my best to help you out. Take it easy.